So we start with our graph of f of x, which is a sine bx plus c, and we also have our graph of g of x, which is a cosine bx plus c. So these share the parameters a, b, and c. So if I make changes to a, it changes the amplitude for both f of x and of g of x. So we have that. What we want to explore is what happens when we change the values of a, b, and c for h of x equals f of x plus g of x. So a sine x bx plus c plus a cosine bx plus c. So I'm going to hide the graphs of a sine bx plus c and a cosine bx plus c. If you just notice that the graph of h of x, which is in purple right here, it has a slightly larger amplitude than the amplitudes of f of x and g of x, and it's also shifted to be kind of right in the middle, for its peak to be right in the middle of the two graphs of f of x and g of x, which is probably because these two functions are added together. So now we're just going to explore what happens when we change the values of a, b, and c for h of x. So we're just going to keep h of x on the screen, and I have the values of a set. I'm going to change this to 20, to positive 20, then do the same here, negative 20 to positive 20, just to have a little bit more variation in the numbers that we're testing for A, B, and C. So we have that. Now we are going to look at h of x, and what happens when we change the values of a, b, and c for h of x, which is f of x plus g. So I'm gonna switch a around, and so it looks like this is changing the amplitude of h of x. So changing a, increasing it increases the amplitude, but also decreasing it increases the amplitude, because it looks like the amplitude is just the absolute value of a, is affected by the absolute value of a, and it doesn't necessarily have anything to do with positives or negatives. So we have that, and I'm going to put this back to 1. For b, let's see what happens when we change b from anywhere between negative 20 to positive 20. And we have decimals included in this. I didn't want to leave decimals out. So here we go. We are changing b. And so when we're changing b, it looks like when b is a really high number, such as negative 20, I mean, that's a low number, but 20 itself, like absolute value of 20, negative 20, that's a high number. When it's 20, it's really compressed, and it seems like the periods are smaller for b, and when we go back to positive 20, it's the same, like it's really getting compressed. But as we move towards smaller numbers, like the absolute value of smaller numbers, like negative 2 or negative 1, b is getting really, the period of this graph is getting really stretched out. So we have something like 0.4. This is getting really, really stretched out. And when we have b equals 0, it's a straight line. So that's an interesting observation. We knew that b in the original graphs of cosine and sine x, um, dictates what the period of the graph is. So this isn't necessarily a surprise, but it's an interesting observation that we have, that it's the absolute value of b is what matters, and not necessarily whether b is negative or positive. It doesn't seem like that matters. As long as the absolute value of the number is high, it seems like the periods are getting smaller. And when the absolute value of the number is decreasing, it seems like the graph gets more stretched out, and the periods are, the size of the periods is decreasing. That's what I meant. And the size of the periods is increasing whenever we have smaller numbers. So there's that. I'm going to put this back to 1. Now see, what our original c was set to 0, but we want to see what happens when we change this number. So now we already knew, and we observed that in the graphs of cosine and sine x, c dictates the horizontal shift of the graph to the left. So let's start back on 0. I know that this graph is being shifted horizontally. I just don't know if there's a pattern in the shifting at all. So I'm just trying to make sure when I switch it from 0 to negative numbers, it's shifting to the right, it looks like. And when we go from 0 to positive numbers, the graph is being shifted to the left. So that's an interesting observation that we have, looking at h of x, the addition of sine x, a sine bx plus c, and a cosine bx plus c, and what changing these values does to the graph. So yeah, decreasing b to, like, the absolute value of b being a small number, it makes sense why the periods are bigger in size, because as you can recall, the periods of cosine and sine are affected by, for sine x, it's the parameter b. You use that to find the period, and the period is 2 pi divided by b. So 2 pi divided by a number that's really close to 0 is going to be a bigger number than 2 pi divided by 20. So it makes sense why this is happening when we change our value for b. And it makes sense why there's a horizontal shift in the graph when we're changing our number for c, because as with most of our parent functions, like such as quadratics or cubics, when we have this inside a or inside piece where we have x and we're adding or subtracting something, there's a shift in what's in how the graph looks like. There's a shift in the graph horizontally, but it moves to the opposite of the sign that is um, that is in front of C. So if C is negative, this we are seeing that it's moving. As C gets more negative, as it decreases, it's moving to the right or to the positive side. But when we have C as positive numbers, it's moving to the negative side. So that also makes sense based on our previous knowledge of just these two functions that we have. And the amplitude A changing whenever we have, whenever we're, whenever we're changing the value for a, the amplitude of the graph changing. That makes sense as well based on what we already know about the graphs of sine and cosine. So yeah, that's my initial observations for h of x equals f of x plus g of x.